Yeah, so in today's lecture, or rather course, we are basically going to look at how you draw structures. That is, if you are given a nomenclature and you're told to give a structure. So now, the same rules that we were applying, that is rule number 1, number 2, number 3, number 4, up to number 5. Relation principal, substituents, double liaison, triple liaison, then you have the alphabetical order, then you have the multiplication factors. Now, the first thing you're supposed to do in all cases, that is if you're given a question to say, give us a structure formula for this, give us a structure formula for, is it 3-ethyl, 4-methyl hexane. What you're supposed to do is first of all, discover or rather find out what the chain principal is. It is from the chain principal that you're going to position these substituents. So our chain principal is hexane. It's a hexane. That is, it has got 6 carbon atoms. It has 6 carbon atoms. Therefore, you're going to draw your chain principal with 6 carbon atoms. So you're going to start with carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. That's your chain principal. Now, the positioning of the alkyl groups, you can position it in any way for as long as they are at position 3 and position number 4. So some can start the positioning from this end towards that end, or some will start from this side and go to the other side. So if you look at mine, I started from this side and I'm going in this direction. So at position number 1, 2, 3, we have an ethyl. An ethyl is drawn, or rather, it is an alkane with 2 carbon atoms and with 1 hydrogen atom less. It is an alkane that is with 2 carbon atoms and with 1 hydrogen atom less. So this is ethyl at position number 3. That is ethyl. Then if you look at the bondings are respected. Always you are supposed to respect the carbon bonding that is with 4 liaison. So for this one, we have 1, this one here 1, we have the second one 2, we have the third one 3, and we have the fourth one that is between the carbon and the hydrogen. So now so we come to this one here 40. So we are going to have this 1, we have this second one 2, and we have 2 of them that are being distributed by the hydrogen atom here. So it sums up to 4. Same applies to the other side. You have 1 and you have 3 more that is adjacent hydrogen. So one. So the idea is for the structure formulae developé, plain or bien semi-developpé, they're just testing you to see if you understand the bond, the number of bonds that a carbon atom has. The number of bonds that a carbon atom has. So upper not pusher. Same applies to this one. So everything here is supposed to respect the rule which states that carbon atom is supposed to have 4 bonds maximum. So this one here also has, this is 1, this is 2, this is 3, plus the other one that is carbon to hydrogen here, 4th one. Then we have another one that is bonded to the methyl at position number 4. That is position number 4. We have methyl, we have 1, we have 3 adjacent hydrogens. So one. And therefore, the nomenclature becomes 3-ethyl because the ethyl is at position number 3 and methyl is at position number 4. Hexane. And hexane is our chain principal. It has got 6 carbon atoms. So the rule is, every time you've been given a formula, say, donner la structure semi-développée ou bien topologique. I do this in the form of semi-développée topologique. If you follow it through, it goes something like this. It goes like that. It's topologique. So they can ask you to do formula topologique. So topologique would be something like this. Like that. Then here, this is 1, 2, 3. You're going to have your ethyl like that. So it's carbon number 1, carbon number 2. Then at position number 4, you're going to have your methyl like that. So I put 2 here. I put the structure semi-développé avec formula, is it topologique? Yeah. Then, is it clear for the first one? Est-ce que c'est clair pour la première? Okay.
It's clear for me.
Okay. So we go to the second one, that is 4-butyl 4-vinyl hept 5 N So like the rule states, we're always supposed to start from our chain principal. Now our chain principal here shows two factors. There's one here that shows the presence of an alkane, and the other one shows the presence of an alkene, the one with a triple liaison. So if in the exercise that you guys were given, there was no positioning of position number 1. If there is no positioning, that is, if it's just written like that, it's written 5 like that. In the exercise, it was something like this. Hept. If you have something like this, just know that the coefficient here is 1. Just know that the coefficient here is 1. So don't be, no, Shana, it's, the coefficient there is just 1. Yeah. So we have two things that we are going to consider. That is a double liaison. This terminaison is for a double liaison for an alkene hybridisation à l'état sp2, then an alkane that is with triple liaison, that is going to be hybridisation à l'état sp. So please, every time when I repeat the hybridisation à l'état sp, these are the questions that they usually pose. They'll ask you to say, okay, in this compound, calculate the hybridization for each carbon atom. Now, the easiest route or the easiest method you're supposed to use is not rather calculating, but using the 3 principles. That is, for a single bond, you are going to have hybridisation à l'état sp3. For a double liaison, you're going to have hybridisation à l'état sp2. At 3, that is a triple liaison, you're going to have hybridisation à l'état sp. Then you're also supposed to know the angles, the bond angles that each hybridization offers. So for hybridisation sp3, you have 109.5 degrees. Hybridisation à l'état sp2, you have 120 degrees. That is triagonal. Then for hybridisation sp, you have got 180 degrees. That is the bond angles. So in a question where I say is calculate hybridisation, here you just say this is sp3, this is going to be sp2, sp2, sp3, sp2, 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 oh, sp3, 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 sp, sp. Without calculating, because there are formulas that you're going to be using, but without calculating, you just look at what liaison exists. You just look at what liaison exists. It's a double liaison. You call it sp2. Is it a single liaison? You call it sp3. If it's a triple liaison, you call it sp. Is it clear? So there are some questions that may be posed to say, what is the hybridization of this carbon atom here? So you calculate, there are formulas that you're going to use, but rather the formulas will just justify the hybridization. If this here is hybridization à sp3, the formula that you're going to have will justify that it's a hybridization sp3. So the other thing that you're supposed to take note when you're calculating, because formulas will just justify what you already know. Yeah. So like I said, the formula when you're calculating, or rather looking for which one is the chain principal, or what the chain is and how the substituents are arranged, you're supposed to look at la chaîne principale premièrement, la chaîne principale. So it is la chaîne principale that is going to help us understand where these are positioned. So la chaîne principale is made up of a double liaison at position number 5 and a triple liaison at position number 1. So what you do is you always just write to carbon, 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 6 of them, 6 carbon atoms. Then you begin positioning these important details. So the first one will be, okay, we are going to position the triple liaison at position number, pardon?
Is it 6 or 7?
It's 6. 1, 2, 3, 4, 5, 6, or 7. Hep 10, 7. 1, 2, 3, 4, 5, 6, 7. Yeah, 7. So you're going to position the first thing you're supposed to do here. Like I said, the rule is when a triple liaison is occurring as number one, you consider that root. If a double liaison is starting, you consider that root. But in a case where you have a double liaison at position number one and a triple liaison at position number two, the double liaison has priorité. The double liaison has a priorité. So in our case, we do not have such a case. We have a triple liaison that's starting, and the double liaison is later on at position number 5. So the triple liaison can either be this side or this side. It depends on where you want to position it. So first of all, I said you just write carbon, 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 carbon. Then you start now appreciating the rule, which is a carbon atom will always have that is 4 liaison. That is 4 liaison. At position number 1, you're going to have a triple liaison. At position number 1, you're going to have a triple liaison to satisfy what we are seeing here for the chaîne principale, to satisfy what we are having here. At position number 5, you count 1, 2, 3, 4, 5. At position number 5, you're going to have a double liaison. 5, 1, that is 5 in. 5 in. At position number 5, you're going to have a double liaison. Then you are done. That is the chaîne principale. You are done with la chaîne principale. What is remaining is the addition of substituents. What is remaining is the addition of substituents. So the first one, if you are to consider this nomenclature, this one here, the first one is butyl. The first one is butyl. So butyl is made up of 4 carbon atoms. That is 1, 2, 3, 4. It's an alkane. Butane is an alkane with 4 carbon atoms. But when it becomes a substituent, it becomes butyl, and it has 1 hydrogen that is less. So at position number 3, you're going to have your butyl. That is 1, 2, 3, 4. Then please take note. This alkane is always supposed to have a hydrogen atom less. It is always supposed to have a hydrogen atom less. It is always supposed to have a hydrogen atom less. So you can even satisfy the formula that is CnH2n plus 2. So if we have 1 hydrogen less, it will be 1. So when you replace the number of hydrogen atoms are supposed to, this formula is supposed to sum up with what you have here. This formula is supposed to sum up with what you have here for the substituent. So butyl is a chain that has 4 carbon atoms, that is 4 carbon atoms, and with 1 hydrogen atom less, with 1 hydrogen atom less. So this is our butyl. Then our vinyl is also known as ethylene. Vinyl. So our vinyl is basically our CnH2n. Now we're saying it's 1 hydrogen atom less. It's 1 hydrogen atom less. Therefore, it's going to be ethene, which is CnH4, C2H4 with 1 hydrogen less. Therefore, it will be 3. It will be 3. And we have 3 here. 1 and the third one there. That is 2 and 3. So the idea is, whenever you've been given a question like this, say, what is our substituent? Always look at the general formula. Then from the general formula, just remove, it is always a hydrogen atom that's going to be less for all substituents. For the ones that have got, is it a double liaison, the ones that have got a triple liaison, the ones that are having a single liaison. Always look at the general formula for each. Then from there, just remove 1 hydrogen atom. Then you will not say, okay, this is an alkane, this is an alcene. So these are the general formulas. So C2N plus 2 CnH2n, that is moins for, and okay, this is for the triple liaison. Then for the double liaison, you're going to have C2 like that. So whenever you have a substituent, you're always going to have a minus hydrogen atom. Always going to have a minus hydrogen atom. So this is our butyl and this is our vinyl. So vinyl is the nom usual. Then the nom is its UPAC is ethenyl ethenyl. So at position number 4 we have 2. That is vinyl, also known as ethenyl, and butyl butyl. So the idea is you're always going to respect the bonds that carbon offers. So you have 1 for this carbon atom here. You have 1, 2, 3, and 4. For this one here, you have 1 with a hydrogen, 2, 3, and 4. For this carbon here, you have 1, 2, then you have 2 here foot. That is 1 for the hydrogen there, and another one for the hydrogen there. So it will be 4. It applies consort. It applies. Here you have 4. Here you also have 4. Here you also have 4. All of them, you have 4 bonds that are being shared. That is for the carbon atom. Any questions? Okay. If there are no questions, we continue. So, allyl ou bien olil, this one is also known as I would call it propenyl. Propenyl. I wouldn't give it the position of the double liaison, but it is a propenyl. So the double liaison can be at position number 1. It can be position number 3. You get it? The double liaison can be at position number 2, that is 1, 2, or it can be at position number 3, depending on how it is bonded. But the idea is that allyl is the same as propenyl. So as time goes on, please also acquaint yourselves with the nom usual, the nom UPAC, because some questions always have those two tricky things, like they want to question you on which, if you really know what the nom usual for this compound is, or the nom UPAC, if you understand what it is and all those things. So that is the reason why even when I was giving the solutions, I was putting both, because it will help you understand where these things are coming from. Because from our lectures, we only had the nom UPAC. We only had this. We only had this. Going like this. So we are saying our oli is the same as a prop de il. So même chose. Our chaîne principale is cyclohexene. Now, cyclohexene, c'est-à-dire you have a double liaison quelque part. You have a double liaison quelque part. So you can have a double liaison there. You can have it 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 there also. It depends where you want to position it. But the double liaison, wherever you're going to position it, this is where your substituent is supposed to come out from. If it is at this position, your substituent is supposed to come out from there. If it's at this position, your substituent is supposed to come out from there. If it's at this position, there, ainsi de suite. Now, I position mine here. That is our double liaison for cyclohexene. So what you also do here, you just draw, that is CH, you draw your carbons. Always draw your carbons. Because once you draw your carbons, you will know that, okay, this carbon is bonded to this carbon, this one is bonded to this one, and this is how many are remaining for us to satisfy the rule. So you just draw, this is how you, I mean, so you draw a carbon there, your carbon there, another carbon here, another carbon there, another carbon there. Then you join them like that. You join them like that. You join them like that. Then you begin now looking for where the double liaison can be. It can be there, or rather can be there. It can be anywhere. So mine is here, which is what we are having here. Now we have an alkyl, or rather a substituent. at position number 1 and at position number 3. So we are saying our double liaison is what gives us direction. Our double liaison is what gives us the direction. So if the double liaison is at this position, if someone is asking, so if the double liaison is at this position, our direction, that is when we're counting, we are supposed to take en compte the 2. We are never supposed to go in that direction. We are supposed to count the 2. We can start from here, that is 1, 2, or rather 1, 2. The idea is we are always supposed to take into consideration the 2 carbon atoms that are engaged in the double liaison. The 2 carbon atoms that are engaged in a double liaison. So some of you might be, okay, we can go like that. That is 1, 2, 3, 4, 5, 6. We can come to this is position number 5. Then some will be like, we can go to 1, 2, 3. That is position number 3. And forever, the rule will always be, we are supposed to give the indice la plus bas to a substituent, or bien the substituent is supposed to have the lowest indice possible. Now, in our case, we have, that is 2 substituents. Now, the first one is at carbon number 1. The first one is at carbon number 1. The first one is at carbon number 1. So our carbon number 1 can either be this one or this one. So if our carbon number 1 is this one here, then our substituent will branch off from here, from there. So this is propene. 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 Now, what happens is when propene loses one hydrogen atom, it becomes propenyl. Propenyl. Don't consider the 2. The 2 is just the position of the double liaison. It can move. It can move. It can be at position number 2. Can be at position number 3. In our case, it's at position number 2. That is 1, 2. We can still have it here at position number 3. But the idea is this is propene. Now with one hydrogen less, with one hydrogen less. So propenyl is the same as this here, onyl. This is onyl. So it is the same thing. That is l'anom usiel, and this is l'anom upac. L'anom upac. So at position number 1, we have this propenyl substituent, or bien a propane substituent. A propane substituent. Then at position number 3, that is, if this is our position number 1, then the direction we're going to take will be this. The direction we're going to take will be that. At position number 3, we have a methyl. At position number 3, we have a methyl. So we can also have another orientation, which is our chain principal is cyclohexane, of course, with a double liaison. We can still have the double liaison positioned at here, positioned here. Our substituent can come from here now. We can still have our substituent coming from here. So please, when you're drawing la structure développée pleine, la structure semi-développée pleine, anything that is convenient with you, you draw it. It's not like there's a specific answer that the professor is looking for. No, anything that is convenient with you. If you want, this double liaison can be positioned this side, and you still have your substituent there or there. It can be here. Your substituent can come out from there, and you can start counting either in this direction or rather this direction. But of course, you are supposed to respect the name. All in all, you're supposed to respect the name. So now we're saying the substituent can actually come out from this carbon atom that is there. Instead of us having our methyl there, we're going to have a methyl here. The methyl will be here. The methyl will be here. So, and our numération will be 1, 2, 3, which is the same thing, which is 3-methyl 1-propenyl, which is 3-methyl, alphabetical order, and 1-propenyl, which is the same as 1-onyl, olyle 3-methyl cyclohexene. It's the same thing. You can still have our substituent, this one, positioned here. So our substituent are represented with a PR to represent the propenyl, and we can still have our methyl still at this position because our numeration, our numeration will be 1, 2, 3. Our methyl will still be there. Or rather, we can still have our propenyl here. And our numeration will be, if this is a propenyl and position number 1, we're going to have 1, 2, 3. And our methyl will be here. So please, it's not like there's only one way you can do this. You can position it at whatever point you want to. You can still have our methyl there, for as long as it satisfies the nomenclature. So if our propenyl is at this position, our substituent will be there. And therefore, here we're going to have a double liaison. We're going to have a double liaison there. Ça va? Est-ce qu'il y a des questions? Okay, ça va.
Daliso.
Yes, madam.
For the allele, I didn't really get you. May you repeat?
Okay, so the anil is also known as prop. Where is the eraser? So anil is the same as what's this? As propenyl. It's the same thing. It's the same thing. It's just that because of the A, that is the rule of alphabetical order, the A comes in first. Now, with the nom UPAC, we are going to use proper de il. So, anil is la norme usuelle. Is la norme usuelle. Just like we had here, we had vinyl. Vinyl is also known as vinyl is also known as what? If you're following. Vinyl.
Ethyl.
Ethenyl.
Oh, ethyl.
Also known as ethenyl. So these things can be used interchangeably. Of course, you can use them interchangeably. So in a question or in an exam, because you guys at the end of the day, you're supposed to be examined concerning how you use these things. In an exam, when you have been given like this, it's a bit hard for you to get what this is going to be because this is the norm usual. So like I said, the advice I gave was, as far as you guys are going to be studying organic chemistry, you are also supposed to look at what these normal or bien norm usual are, because they can also give you an example would be, they can give you vinyl here. They can just say un vinyl 3-methyl cyclohexane. Now, if you don't know what vinyl is, it will be hard because without the nom UPAC, you can't really draw the structure. The nom UPAC, if you've noticed, the nom UPAC is always giving us a hint on how many carbon atoms we are going to have. Take it, for example, propenyl here, you have got 3 carbon atoms. Ethenyl, you have 2 carbon atoms. Methylidene, you're going to have that is 2 carbon atoms. If it's going to be butenyl, you're going to have 4 carbon atoms, but with always 1 hydrogen atom that is going to be less. That is the idea. So what I'm trying to say is the norm usual will never be taught in one way, but we are supposed to know the norm usual of these different substituents. So anil is also known as a propenyl. So it is through la chaîne ou bien la norme UPAC that is where we can deduce to say, okay, no, anil is the same as a propenyl. And therefore, if it's propenyl, we have 3 carbon atoms. That is for an alkene with 1 hydrogen atom that is less, because it's a substituent. In this case, it's acting as a substituent. So all substituents will always have 1 hydrogen atom less. We always have 1 hydrogen atom less. Now, maybe let me just explain a bit of why we are calling it one hydrogen atom less. The carbon atom has got 4 bonds. The carbon atom has 4 bonds. The carbon atom has 4 bonds. Now, for us to attach something, to it, that is, I'll call this beta. For us to attach a beta or substituent to it, there is supposed to be an atom that is going to be lost. There is supposed to be an atom that is going to be lost. And therefore, for each carbon atom that you're going to have in a substituent, you're going to have a hydrogen atom that is going to be less. A hydrogen atom that is going to be less. So in a case where we have one hydrogen there, another hydrogen there, we have another hydrogen there, we have another hydrogen there. Normalement, we are calling this methane. But when there is one hydrogen, or rather there is a substituent is like, how can I put it? Like it's a joint. Now, a substituent will always will have a hydrogen atom that is less, because substituents will always be built from the number of carbon atoms that each has, or bien from la chaîne principale, from different families. And those families are only the alkenes, that is the double liaison alkenes, the single liaison, and alkenes, the triple liaison. Those are the only substituents you're going to have, unless you are going to talk about the aromatic hydrocarbons and all those things. But the idea is these are the only ones that you're going to have. And in all cases, you're going to have a hydrogen atom that is going to be less. So we're saying the carbon atom has got a maximum of 4 bonds. Now, when you have got one hydrogen less, when we say one hydrogen less, it's not like we are removing the hydrogen. We're actually replacing that hydrogen with another component. We have another component. And because there is one hydrogen atom that is less, it's now going to be called a substituent. So maybe this beta, or this component that we are adding here, is a chaîne principale. Take for instance, this is maybe a benzene ring. If this is a benzene ring, it will be called methyl benzene. You get it, eh? It's going to be called methyl benzene. So the idea is the substituent is just like maybe I'll say a key and lock theorem hypothesis. The key is the substituent, and the lock where we are placing in this substituent is our chaîne principale. So it's just fitting there. When it's fitting there, there is a hydrogen atom that we are replacing, because our alkenes, our alkyls, all those things, they're always going to come from the 3 classes. That is the ones with a single liaison, the ones with a double liaison, and the ones with a triple liaison. So is it clear, Taonga, with where the anil and propenyl come in? This one is just lanom uziel, and this one is lanom upac. This one is our nom upac. So the bottom line is, in all cases, when you are given a question with a nom uziel, you are supposed to, or it's a must that you're not supposed to know what the nom upac is, because it's from the nom upac that is going to help you understand how many carbon atoms that this substituent has. Because from this one, I tell you, you can't even know how many atoms this substituent has unless you know la nom upac. La nom uziel will never tell you how many carbon atoms its substituent has. C'est clair? Est-ce que c'est clair?
C'est clair.
Alhamdulillah. Is it clear for everyone? Est-ce que c'est clair pour tout le monde? Ok. On forge ahead. It's okay. We have another example here. So, chaîne principale, always please, always la chaîne principale. So this is a hept. So it's a hept. It means we have got 7 carbon atoms. So you draw your 7, 1, 2 to 7. You draw them like that. So this is my advice. You draw them just like that, just to draw them like that. Carbon, 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 like that. So this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So you have another carbon there. So you are 7. This is what you should be doing. Draw the carbon skeleton first. The skeleton. you draw it. Then later on, you fix in. So we have a substituent that is, or rather a double liaison at position number 2, and at position number 3, we have that's a triple liaison. So we start from any end, either this side or rather this side. So what I would do is I'll start on the other side because this one here, we started from this side. So you're going to have 1, 2. So at position number 2, you have a double liaison. You draw a double liaison. Then at position number 4, because we have taken the double liaison as a prioritaire, that is going to give us the direction in which we are supposed to flow. So this is 1, 2, we have a double liaison, 3, and 4. We're going to have a triple liaison. A triple liaison. Then you add in your hydrogens, add your hydrogen, 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 hydrogen. Satisfy the carbon rule. Then, before we conclude, you are going to also include your substituents. Your substituent. Now, another thing here, we have non-usual, non-usual, non-usual. Now, here, the goodness that the non-usual that we have has got another indicator. It has another indicator. The indicator that we have here, the indicator that we are having is the propyl. Propyl. It shows that there are there are 3 carbon atoms. It shows that there are 3 carbon atoms. The iso is just to show that it's an isomer of propane or propene, whatever it might be, but it has 3 carbon atoms. So now where is the propyl, is a propyl bonded to, or where is the substituent? Where is the substituent? The substituent is at position number 4. Sorry, number 3. So this is 1, this is 2, and number 3. We have a substituent. So we call this substituent beta. So the substituent beta is isopropyl. Isopropyl. So isopropyl selon UPAC. Isopropyl selon UPAC is called a methyl ethyl. A methyl ethyl. So this is how you do it. This is carbon number. This carbon here is bonded to this one, tephu. This is our carbon number 1. And we can go either in this direction or rather in this direction. So this is carbon number 1, and this is going to be carbon number 2. So this is our chain principal. This is our chain principal. So we're calling this ethane. We're calling this ethane. Tephu. We're calling this ethane. And we have a substituent at position number 1. So we're going to have a methyl ethane. Now, this would have been the nomenclature for this thing here, isopropyl. If we were to give the nomenclature for just this thing here, we would have called it methyl ethane. Now, the problem is this whole thing is not just a chain, but it is a substituent. It is a substituent. And therefore, instead of us having a methyl ethane, we are going to have ethyl. Now, why ethyl other than ethane? It's because we are dealing with a substituent. In our case, this is not just a chain, but it is attached to another chain principal, and therefore it becomes a substituent. So in other words, isopropyl is also known as a methyl ethyl. A methyl ethyl. So in the same sense, you are supposed to know what these non-selon UPAC are for different substituents. You're going to have sec-butyl, you're going to have isopropyl, you're going to have tessio-butyl, all those things. You're supposed to know that, okay, for tessio, you have a carbon atom bonded to 4 different substituents. That is a carbon that is asymmetric. Then for, sec-butyl, maybe at position number 2, you're going to have this kind of orientation. So all these names, they have in the polycoptescent, the Cascan polycoptescent, There's a table where you have all these substituents and their norm you pack and their norm UCL. So as time goes on, you practice with those names because names change. Names will change. They will give you isopropyl and we expect you to draw this structure. So if you do not understand what isopropyl is, drawing this structure will be difficult because it's the only substituent that you have that is isopropyl. But now how to draw it? You'll be like, how am I going to draw it? So you're also supposed to know la norme selon UPAC. La norme selon UPAC. So we are saying isopropyl is also known as amethyl ethyl, amethyl ethyl. Any question? Methyl ethyl. So like I said, this is where I wanted you to get it clearly. So isopropyl, if we're to just name this thing here, just naming it, la chaîne principale will either be this one here, this direction. It can either be this one. La chaîne principale can be this, or it can be this. Don't forget, we don't count this carbon atom because it's in the chain principal. The substituent is where we start from, where the branch comes from. So we call this our chain principal. So our chain principal has how many carbon atoms? That is 1 and 2. Now, what do you call an alkane with 2 carbon atoms? You call it ethane. Now, there is another substituent that is bonded to this ethane, and this is what we are calling our methyl. And is at position number what? If we are saying this is position number 2, and this is position number 3, and this is our chain principal. Therefore, at position number 1, we have a methyl. At position number 1, we have a methyl. We have a methyl there. So we are saying if this was just a chain that we were taught to name, we would have named it methyl ethane. But now because it appears to be a substituent, it will therefore be called methyl ethyl, other than ethane, but ethyl. Est-ce que c'est clair? Est-ce que c'est clair? Tingo sirize pangono pangono ka? Pangono pangono. Tingo sirize. Est-ce que c'est clair? Ok. J'espère que c'est clair pour tout le monde.
Oui.
On continue. Okay. You guys are hot in organic chemistry now, eh? So always la chaîne principale has that is a cyclopropane. It's a cycle. Therefore, cyclopropane. So it's a triangle orientation with 3 carbon atoms. Like that. Then we're saying at position number 1 we have ethyl, and position number 2 we have methyl. So it'll be where, okay, position number 1 we have methyl CH3, and encore at position number 1 we have a So some of you might have this question and ask me, say, Del, so is it okay if you were to write H to write this? Some will ask, okay, is it okay if you were to write this CS3 like that and write like this? How can I put it? That is CH2. So H2 CH3. Bien sûr, c'est la même chose. It's just that with this one, I just want to show that, okay, this carbon atom is bonded to this carbon atom, and this carbon atom is bonding to this one. So these two, c'est la même chose. And don't forget, always, when you're doing your structures, you put your number of carbon atoms that will be found there. 2, and here you already have 4. That is 1, 2, 3, and 4. So this is un éthyl, un méthyl. C'est clair? Est-ce que c'est clair?
C'est clair.
Tonga, it's like you're the one answering. Is it clear for everyone?
Yes.
Alhamdulillah, alhamdulillah. I think this is the last one. N'est-ce pas? C'est la dernière. So, comme toujours, la chaîne principale is what you consider. So, like I said, please, when you go to school, this is what you should be doing always. When you're taught to give a structure développée, ou bien compact, ou bien topologique, always do this. Draw your carbons first. How many are there? Hexane, hexa. There are 5 or 6. You draw 6 of them. You draw 6 of them. 1, 2, 3, 4, 5, 6. Hey, that's not rule number 1. Rule number 2 would be look at what is happening. Okay, you're saying at position number 1 you have a double liaison. Looking at the terminaison here, the suffix, suffix. You're looking at the suffix, so you have a double liaison that is at position number 1 and position number 2. So and 5, sorry. So position number 1, we have a double liaison, and at position number 5, that is 1, 2, 3, 4, 5. At position number 5, we have another double liaison. So with la chaîne principale, c'est bon, you are done. Now you look at what's remaining here. What's remaining? Now what's remaining here is an auxanyl. This is a substituent derived from an alkyl with a triple liaison orientation sp hybridization, bond angle 180 degrees. Then with is a topologique that is linear. That is, if they ask you for la structure théorique de la molecule, if it is having a triple liaison, you call it linear. It's a double liaison, you call it triagonal. If it's a single liaison, that is sp3 hybridization, you call it tetraedric. So in chimie, on liaison chimique, we looked at these theories. That is the Vespa's theory, the valence share electron repulsion theories. Those things also, please take into consideration. It's not always that you're going to have the triagonal, tetraedric, and linear. You're also going to have those bipyramidal, tetraedric, all those things. Please take note, they can also apply. But for organic chemistry, seulement for organic chemistry, you only have these 3. You only have sp3, sp2, and sp. That's all. You only have these 3. This is what you'll be playing around. But for chimie en solution, chimie générale, en chimie générale, vous allez avoir sp2 hybridisation, sp3, sp, and any other hybridization, because the formation of those repulsion theories is from the different hybridizations that you're going to have. Not only sp3, sp2, sp, there are also other types of hybridization that you're going to look at, but the basis of hybridization is the same. The dégénération des énergies, it's always the same. There's an energy level that's going to degenerate. The degeneration of an energy level is basically the having of 2 energy levels. If this is a p orbital and this is a d orbital, them coming together at the same energy, if this is what we're going to call energy 1, if both of them are at energy number 1, like that, if they're at energy number 1, this is what we're calling dégénération des orbitales. Dégénération des orbitales. So in other words, hybridization is derived from the dégénération des orbitales. Dégénération des orbitales. So we continue and close. Then we are saying this is an auxanyl with that is 2 carbon atoms, triple liaison there, and you have one hydrogen atom less. Acetylene is the simplest, that is C2H2. Now, if we remove one hydrogen atom, it becomes a substituent. It becomes a substituent. So we're going to attach this substituent to our number 3. So this is 1, 2, 3. We're going to have our CH like that. So never forget to put your carbons. The hydrogens are never hard to replace, because if you just count if it has respected the number of bonds. So is it clear for all the questions that we have done so far? Is it clear?
Yes, it is for me.
Okay. So are there any other questions? Because I was told this is the part that you guys had problems with, the drawing of structures. The nomenclature part, I guess you guys are okay with it, where you have la chaîne and you're told to name it. Steph, and moreover, we only did the part of nomenclature. We didn't do nomenclature complete. Then the other thing that we just forgot, or rather we did not do, was the nomenclature selon, is it SIP, can, in, God, and the prelog system. That's the only nomenclature we did not do, but I explained a bit on how you go about it. That is the orientation in the clockwise direction. That is what you're calling the arrow orientation, and the anti-clockwise, which you're calling the S orientation. And of course, about the carbon that is asymmetric surf. So a carbon that is asymmetric is one that has 4 different substituents bonded to it. So maybe just to add on those things, I'll just use some of the examples that you have here to just add on, because I guess this is the last time you're hearing anything from me. Yeah. So when they ask you to say which carbon here is asymmetric, which carbon is asymmetric? So a carbon that is asymmetric is that has 4 different substituents. And please, attention, there will never be a carbon that is going to be asymmetric, that is with a double liaison. If you have a double liaison, you forget about that carbon being asymmetric. So these two automatically are ruled out. They are not asymmetric. So this carbon here is asymmetric in the sense that it has got this substituent 1, this substituent number 2, and this substituent number 3, and forgetting the hydrogen here, number 4. So for a carbon that is asymmetric, we put a star. So you show that this carbon is asymmetric. Then if it is la nomenclature S or bien la nomenclature R, you're also going to look at the same thing. So I'm just revising maybe with the things that we did last time. I'm just like a resume. So you have this substituent, this one here, and this one there. So you're going to look at priorité. So with priorité here, I'll just give priorité to each of them to just facilitate understanding. So I'll give this one 1, I'll give this one 2, I'll give this one 3, and give the hydrogen that is always number 4. That is the priorité series. This priorité that I've given here is just imposed. Normalement, you are supposed to look at which one is the priorité, that one that comes first. So I've just imposed, just give meaning to what it means to come up with nomenclature selon SIP. So if we are moving in this type of orientation, what do you call this orientation? Is it clockwise or anti-clockwise? This orientation. Is it clockwise or anti-clockwise? Pankoloko, what do you call this orientation? Is it clockwise or anti-clockwise?
Clockwise.
We call it clockwise. So we said selon clockwise. If it's clockwise, if your clock is like that, and you have this orientation like that, we call it the arrow orientation. Now, if you have this, I'll do it, orientation, where you're moving in the opposite direction, you have the anti-clockwise, that is the S orientation. Now, this orientation here is what you are calling the clockwise orientation, and therefore it will be called R. And so if we're going to give the name of this organic compound, selon UPAC, it will be R in brackets. Then you're going to have this here. You're going to have this here. And please, like I said, when you've been given a question, you also look at the question that you've been given. If you've been given a question that is like this, never use SIP. Never look for which one is prioritaire and therefore look for the chain prioritaire, the one that is more prioritaire. Never. If it's drawn like this, if it's drawn like this, you never look for la chaîne prioritaire, then you'll be like, no, clockwise, anti-clockwise. No. For a chain where we use la principal SIP, is this one here. Let me show you. Molecules like if
It's 6 o'clock.
You have a carbon atom there. You have, say, substituent there. You have one on a dash, maybe say NH2. You have another one there. Then here you have a wedge for CH3. In such type of an arrangement where you have a dash and a wedge on, is it a wedge and a wedge on dashes? This is what we're calling a wedge, and this is what we're calling a wedge on dashes. If you have this type of arrangement and they tell you to nommer selon UPAC, this is where you apply the SIP. You look at which one is prioritaire, you move in the clockwise or anti-clockwise direction, depending on the carbon that is asymmetric. Depending on a carbon that is asymmetric. Then to just sum it all, there will be questions that will be asked after finding out if a carbon is asymmetric and all those things. Questions will be like, how many stereoisomers does this organic compound have? So the number of stereoisomers an organic compound will have is dependent on the number of carbon atoms that it has that are asymmetric. So the formula is 2 à la puissance n, where n will be equals to the carbon asymmetric. So carbon asymmetric, I said, is represented with a star. With a star. So this is the number of stereoisomers. Stereoisomers. Then for, okay, I'll end here. I won't go in much details. This is the number of stereoisomers. And to conclude it all, there are going to be questions as well on finding out if a compound is chiral or bien achiral. So the notion is, if a compound is chiral, it should never be superposable with its image. That is, the enantiomer should never be superposable with its object, or rather the image and the object are not supposed to be superposable. And the second one is, there should be never, ever a plane of symmetry, or rather an element of symmetry. There should be never be superposition of two images, that is an image of an enantiomer with the object, and the superposition, le plan de symétrie, that is a plan de symétrie for the whole molecule, ou bien une symétrie selon un élément. Selon un élément. So if there are no questions, we close here. And wish you guys all the best in your studies. And for those that we are going to meet, inshallah, we shall meet and discuss how organic chemistry was in the faculty. So if there are no questions, please, you can still ask me questions. You can still, there are people that I was teaching chemistry last year, they still ask me questions on how to go about certain things. So feel free, when you have a question, when you're going to school, things might not be straightforward at the first instance. So you may still have problems on one or two things. Feel free to ask me. Feel free. If you have my line, ask me. If you don't have my line, you'll get it from the group. Please still ask me. Say, no, I don't understand what is happening here, so that I help where I can. Where I can't, I'll tell you, okay, no, this one I can't because this one we are not going to, we didn't do, or maybe I don't understand what this is all about. But or more, anything that you have, like if you have a question, for those that are having organic chemistry, those that are going to have, for answer, you're going to have crystallography and chimie organique and atomistic all together. So for those guys going to answer, that is atomistic, is it organic and crystallography. You can still ask me questions on those things. Those that are going to go for medicine, you can still ask questions on mineral. No, sorry. You can still ask questions on organic and biochimie. Now, biochimie, I'm only restricted with biochimie structurelle. Biochimie structurelle. Metabolic, I didn't go as far as metabolic, so I only went as far as structurelle. So for those doing medicine, those are the courses that you can ask me. Those going for SVT also, you can still ask me questions on organic chemistry, is it chimie or solution? In other words, you can ask me any question with any subject that deals with chemistry, any subject that deals with chemistry. So you let me know, say, okay, I'm doing this type of chemistry, and I'll let you know, say, okay, I did this type of chemistry and I can help. But if I did not do it, I can still find ways in which I can explain one way or another. At the end of the day, I'm still also learning how to go about my chemistry, and you guys are also learning about your chemistry as well. So if you have no questions, please persevere and all the best in your studies.
Thank you.